Now what we're asked to do here is show that f is a root between 0 and 1. Now we know it's going to have a root between 0 and 1 if it changes sign. I'll just draw this just to explain to you a bit better. So say we have our x graph here and our y graph here, and we have 0 the origin here, then we have 1, then we have 2. Now just say for instance we're going to have the graph going downwards rather than upwards. It doesn't really make a difference. So we just draw it going downwards. Now at x equal to 0, y is going to be positive, and at x equal to 1, our y value is going to be negative. Therefore we know that the graph actually crosses through this point. So if we fill in a value of x equal to 0 and get a positive result, and then a value for x equal to y and get a positive or negative result, or vice versa, then we know that the line actually runs through between 0 and 1. So that's what we'll do. We start off at x equal to 0. 0. Dash f of 0 is equal to negative 1, which is a negative number. Now we're going to try at x equal to 1. That applies to f of 1 is equal to 32 minus 48 plus 20 minus 1. And that is equal to 52 minus 49 is equal to positive 3. So because it changes sign, because our y value changes sign between 0 and 1, that means the graph crosses between the x-axis between points 0 and 1. And as we see here, f of 0 is equal to minus 1, and then f of 1 is equal to positive 3. So that's just the graph's actually going upwards like that. Your 0 value here, your 1 value here. So that's the way the graph goes. On to the next question now. We're asked a Newton-Raphson question. Now these questions are actually very straightforward, so if one of these did pop up with a differentiation question, I definitely recommend doing it. Like once you know the formula, there's really very little that can go wrong apart from your layout really. So I just have the formula written down here. So say our second approximation is equal to the first approximation minus f, the function of the first approximation divided by the derivative of the first approximation. So what we're going to do first here is we're just going to get the derivative of f of x. So that's f dash x. That's equal to 96x squared minus 96x plus 20. Now, we have x1 is equal to 0.5. So we're going to have that implies x2 is equal to 0.5 minus f of xn. So our xn is going to be 0.5. 0.5 all to the cubed minus 48 times 0.5 squared plus 10 minus 1, which is 9, and that is all over f dash xn. So that's 0.5 filled in here, so it's 96 times 0.5 squared minus 96 times 0.5 plus 2. Now, I've actually got this worked out earlier. It's equal to negative a quarter here on the right hand side. I'm just to save space. So x2 is equal to 0.5. Subtract negative a quarter is equal to 0.75. So that's our answer here for x2. Now we know our x3 equal to our approximation before that, which is 0.75 minus f of xn of 0.75 all over f dash 0.75. So it implies x3 is equal to 32 times, sorry, 0.75 minus bracket 32 times 0.75 all to the cube minus 48 times 0.75 squared, and so on and so forth. All that divided by your f dash of 0.75, which is 96 times 0.75 squared minus 96 times 0.75 plus 20. And that works out to be 0.5. So it's 0.75 minus 0.5 over 2. Oh, sorry, 0.5 over 2. And that implies your x3 is equal to 0.5. So then so your x2 is equal to 0.75, and then your x3 is equal to 0.5. And the next question is, what do you conclude about all further approximations? Well, you can actually conclude, you can do the next one if you want, but your next one is going to be equal to 0.75, and the one after that is going to equal to 0.5. So you conclude that your next approximations are going to oscillate between one point and the other, and they're going to continuously alternate between these two numbers until we get to infinity.